my task is to give you an overview about how AI ECG algorithms work, and hopefully I'll try and do that over the next 10, 12 minutes. I know Manolis has a complimentary talk, and hopefully between us, we'll give you a good idea of how these things work. So as Sunil says, this is the ECG. It's a humble ECG. We all think we know it. We all read thousands or tens of thousands per year, and we think we're experts. It's been around for over 100 years, or around 100 years. And as an electrophysiologist, I think I'm pretty good at it. But actually, it turns out we're not so good at it. So when I teach medical students about ECGs, I often have a framework in my mind, and I teach them to go through a very set series of steps. So I say, look at the P wave, that's atrial depolarization. Look at the PR interval, that's the AV node. Look at the QRS, that's ventricular depolarization. Look at the QT interval, that's ventricular repolarization. And that has been very helpful for humans to have a framework to understand the ECG. And we've used that framework to our advantage for many years. But at the same time, I think that framework has really restricted us from unleashing the full power of the ECG, because we are trapped by very strict ways of how to look at and interpret the ECG. Now, AI is not constrained by 100 years of human knowledge. It doesn't really care what I think about the P wave or QRS and what's important and what's not important. It reimagines how to look at the ECG in its own way. So what it'll do is it'll make its own mind up about what's important, not what the human says. You'll look at things like the QR interval, the P plus the QRS, and all kinds of combinations of the ECG, often in nonlinear combinations, to make up its mind. So what is AI? I think we all know what is AI, but AI simplistically is the simulation of human intelligence in machines that are programmed to think and act like humans. But AI is quite a broad concept. Within AI, there is simple AI, which is rules-based AI, where you program some rules. There's machine learning, simple machine learning. And a lot of AI ECG actually revolves around deep learning, which is what I'll talk about now. And most of the papers that you read in the literature and talks that you hear about AI ECG involve deep learning as a subset of broader artificial intelligence. So what is the difference between traditional programming and deep learning, which is what we talk about in terms of AI ECG? It comes down to who defines the rules. So in traditional programming, the human defines the rules. So we as humans have learned things over the last 100 years, and we tell the program what to look for. So for example, if you want to look at people with normal or abnormal ventricular depolarization, you might write a script to say, look at the QRS. If it's more than 120 milliseconds, call that abnormal. If it's less than that, call that normal. But the key thing here is the human has defined the rules, and therefore we are entirely limited to what the human has learned over the last 100 years. For machine learning and deep learning, this flips the paradigm on its head entirely. It doesn't care what the human knows or does not know. So instead of feeding rules and data, instead we feed it a lot of data and a lot of answers. For example, you might feed a lot of ECGs into the model, and you might also give it an answer to say whether the person's dead or alive in 5 years. The model will then learn new rules to associate death or alive status in 5 years and the ECG. So this overcomes the limitation of what the human knows, because it learns new rules about what is important in predicting whether someone might be dead or alive in 5 years. And that's the beauty of AI ECG, is we are reinventing the ECG with the machine learning new rules about the ECG that potentially the humans may not have been aware previously. How does it actually work? So the vast majority of AI ECG models use something called convolutional neural network, and this is something that we've taken from computer vision. So say you have a task and you want to train a model to differentiate circles from crosses, a very simple task. What you need to do merely is to provide the model with a lot of circles and tell the model these are circles, and give the model a lot of crosses and say these are crosses. And that's really all the human really needs to do. You can tweak all kinds of hyperparameters to try and make the model become more efficient or let it learn more about the task. But really, These things are set up in such a way that you just need to give it labeled data. So give it a lot of crosses and a lot of circles, and without telling it any rules. And what it does, these CNNs break down the image into small constituent parts by sliding kernels across the image. So in this example, it's sort of broken down the image into horizontal, vertical, and diagonal lines. And without the human telling it any more information, except for knowing which are crosses and circles, it will, over multiple rounds of training, learn by itself that if it sees horizontal, vertical, and diagonal lines, that's going to be a circle. And if it only sees diagonal lines, but no horizontal or vertical lines, that's going to be a cross. And that's how the model has learned on its own what's a circle and what's a cross, without the human ever needing to tell it any information. And it will do this very quickly, and after a short time, if you give it a cross or a circle that is not seen, it will be able to tell you which is which. So you can see you can expand that concept to an ECG. Instead of differentiating, say, a circle and a cross, you might show it lots of right and left bundle branch blocks without telling it this rule about looking at whether it's negative or positive in V1. You just say, these are 1,000 left bundle branch blocks, and these are 1,000 right bundle branch blocks. And again, you don't need to do anything more. And over multiple rounds of training and the machine learning what's important, it will have learned that V1 pointing downwards is generally left bundle branch block, and V1 with this M shape is generally right bundle branch block. And again, over time, it will very quickly be able to distinguish this. In fact, this is the task we give medical students when they join the lab. We say, can you train a model to distinguish left and right bundle branch block? And often they do it with very high accuracy. You can increase and scale up the complexity using the exact same concepts. You might say, well, let's try and show it normal and abnormal LVEF. Again, you do that without telling it any rules, by just giving it 10,000 normal LVEF and 10,000 abnormal EF ECGs. And again, it will on its own learn to distinguish the two. And more complex, you might even get it to predict future disease. So you give it lots of ECGs with those that develop future disease or those that stay healthy over the next 5 years. And again, it can learn the patterns that distinguish between the two. And that really is the underlying sort of building block of how AI ECG generally works. They're all convolutional neural networks, and all the human needs to do is supply the model with a lot of well-curated, well-labeled data, and it kind of will do its own thing. So I'm going to give you a couple of examples of what you can train a model to predict that may not be that initially instinctively useful. So you could train a model to predict someone's body mass index. So I've said to you, all you need to do is label the data, and the model will learn to recognize features associated with the label. So one thing we did was to say, can you train a model to predict whether someone is fat or thin from the ECG? So the label is only the body mass index. And it turns out these things work pretty well. So if you give it enough data, in this case, 100,000 ECGs, with the only label being their body mass index, after time, the model can predict roughly what the actual body mass index is. So something that as an EP, I would never dream of ever trying to predict someone's BMI from the ECG. The model has over time learned the features of a fat person and a thin person. More interestingly, this appears to be a very important biomarker. So when it gets it wrong, it's not because it's got it wrong, it's because it's seeing features of a fat person in the ECG. So for example, my BMI is 26, but the model thinks it's 29. It's not because it's got it wrong, it's because my ECG suggests that I'm fatter than I actually really am, and therefore I might carry more cardiovascular and cardiometabolic risk. And this concept of delta BMI, which is the difference between what is predicted and the real BMI, actually holds important information about risk. So if we look at people with delta BMI and follow them out over 20 years, and this is retrospective data, apparently the greater the discrepancies, so the more the model thinks you're fatter when you're thin, the more diabetes, hypertension, and lipid disorders you have over many years. So here's an example of how you can train a model using something that is easily measured, like body mass index, and actually use that as a useful biomarker. And without going into detail, we did a lot of work using phenome-wide association to look at what the model is actually doing, as picking up things that we associate with cardiometabolic risk, like triglyceride level, pericardial fat, trunk, waist circumference, and so on and so forth. Just another example before I hand over to Manolis. So you can also train an ECG to predict someone's sex. Again, as an electrophysiologist, I would never be able to do that. But if you give it tens of thousands of male ECGs and say these are from males, and you give it tens of thousands of ECGs from females and say these are from females, the model can learn very quickly with very high accuracy how to predict whether someone's male or female from the ECG. And it turns out it gets it between 90 to 100% right, so about 95% AUROC. And it's incredible accuracy. So I would never be able to guess from an ECG whether someone's male or female, but it's clearly learned some rules to associate the QT interval with the Q and the R axis, and it can make these classifications very quickly. I won't go into detail, but we did some explainability analysis to look at how it's doing this. But essentially, it's looking at a combination of different things. So it's looking at QT interval, QRS duration, voltage, axis, and it's clearly a signature of what a male ECG looks like and a signature of what a female ECGs look like. And you can train a model to do that. Obviously, it's not anything we want to do, but you can train a model to do that, and it does it really, really well. Again, I told you about this delta BMI thing, where if it gets it wrong, there's some meaning in it. There is a meaning here if it gets it wrong. So if you're male and the model thinks you're female, or if you're female and the model thinks you're male, there is a biological significance to that misclassification. So if you're male, and it should be males are 0, and it thinks you're between a male and a female, you have a sex discordance score of 0.3. If you're female, it should be 1, and it thinks you're 0.75, there's a sex discordance score of 0.25. So what we did was to say, if the model gets your sex wrong, is that a bad thing for you? And it turns out it is. So the more the model guesses your sex wrong, the greater your chances of dying in the future from all kinds of things. And that might be intuitive, because if you have lots of abnormalities in ECG, it makes it more difficult to guess your sex. But if you restrict it just to normal ECGs, here's where it gets interesting. And I think this fits in with our understanding of biology and cardiovascular risk. If you're male and the model thinks you're female, you do not have any increased cardiovascular risk. But if you're male and the model thinks if you're female and the model thinks you're male, then you have an increased cardiovascular risk. So females with a male-looking ECG are at greater risk of cardiovascular disease, but males with a female-looking ECG do not have the elevated risk. And that's an interesting dichotomy, which gives us some insight about biology. And just for interest, I can show. So males who have a female-looking ECG have a lot more liver disease, but females with male-looking ECGs have a lot more cardiac conditions, so heart failure, myocardial infarction, cardiomyopathy, so on and so forth. So those are just a couple of examples. I hopefully have given you a sort of intro to how AIG works, how you can train it to predict all kinds of things. Obviously, we're interested in predicting disease, but I gave you 2 odd examples, predicting body mass index and sex, and it seems to do that quite well. At this stage, I hand over to Manolis to sort of pick up on the fundamentals, and we'll have some discussion afterwards. Thank you.